Alright, data. So which set can be described as categorical and nominal. Categorical just means it's not a number or not a numerical sort of thing. Nominal means there's no rank to it. Okay, so these are numbers, so let's scratch them. Not that one, not that one. We can't have a rank to it, or small, medium, large is a rank, so not that one. So it's this one. Okay, so no rank, not a number. Okay, sale prices for properties in a suburb. So this was house prices or something like that. So on 1st of August, another property in the same suburb was sold for over $1 million, so really, really expensive. And the question is, if this property was part of this data set, what would it have had on this set of prices? Well, of course the average would change, right? Because if you throw in like $1 million house, well, the average gets pushed up then. Okay, so mean has to change. Will the median change? So if you add on this extra number here, right, like this really, really expensive house, will the median change? Well, let's get the median. If this weren't there, the median would be crossing, crossing, crossing. It'd be halfway between these two. Well, that's just going to be 607,000. But if you had that there, you do the same thing. Well, hang on, the median is still 607,000, so it won't change. Okay, so that means that the mean would change, but the median stays the same. Okay, 6 data values that has a range of 12, mode of 12, well, everything's 12 except the mean. Okay, so minimum value is 12, that's nice. It's 6 things, so 1, 2, 3, 1, 2, 3, 4, 5, and 6, the last one there. Okay, the mode has to be 12, so there'll be a lot of 12s. The median's also 12, so I better put 12 there. I better put 12 there. I better put 12 there as well, because that's the only way the median can be 12, is if it's halfway between 12 and 12. So now the range is 12, which means the distance from this to that is 12. And so that tells me that the last number better be 24. And so finally the mean's got to be 15, so what has to go there? Well, 12 plus 12 plus 12 plus 12 plus that blank number plus 24, when I average them, so divide that by 6, I better get 15. Okay, so what number must go there? Well, 4 12s and 24 give me 72. So 72 plus that number over 6 equals 15, right? Which means that 72 plus that number must equal, how do I kill it over 6? I need to times by 6. So I get 90, which means this number must be 18. Okay, so that's the way we can work that one out. Okay, so mode is 12, median's 12, that tells you that it's all 12s up to and even a bit past that halfway point. The range gets you 24, and the last number you can determine by using the mean being 15. Okay, like we did on the right with all the green stuff. Okay. 7 employees earn the following wages. Is 970 an outlier? Justify with calculations. So, outlier stuff, this is on your formula sheet. I think it's the most useful thing on your formula sheet because it's clear what it does. Okay, so outlier is either too big or too small. Now, 970 is of course only at risk of being too big. Okay, and your formula sheet will tell you this, that an outlier, okay, is too big, okay, if it is past Q3 plus 1.5 times the interquartile range. It's all about the quartiles. So we've got to find these quartiles first. Okay, so first let's get the median, the middle number. Okay, you cross off the ends, middle number is 590. So let's ignore that for now. We don't need that one. Okay, we have two data sets now, the left and the right. We get the median of each of these ones. Okay, so the median of the left is 490, median of the right is 680. So it tells you that Q3 is 680. Okay, and what's the interquartile range? The interquartile range is the difference between these two quartiles. So 680 minus 490, which is, I'm running out of room, I should have written this on the left, that's 190 as well. Okay, so that means this 970 is an outlier. The cutoff point for when it's too big is if it's past Q3 plus 1.5 interquartile ranges. So it's going to be 680 plus 1.5 lots of interquartile range, that difference between those quartiles, which was 190. So I get 680 plus 1.5 times 190, and I get 965. So anything past 965 is an outlier, and 970 is past 965, which means that 970 is an outlier. Okay. Alright. Each employee receives a $20 pay increase. What effect would this have on the interquartile range? Well, if every one of these numbers gets bumped up by 20, would the difference between these two change? Right, if everything was bumped up by the same amount, okay, when you're comparing two numbers, they won't be, like, the difference won't change then, right? So that means this has no change. Alright. Set of exam results as percentages is displayed in a frequency histogram and polygon. What's the median? Well, cumulative frequency is a running total of all those marks, and the very end of that is 50, which means there are 50 marks or 50 scores altogether. Median would be halfway up. Okay, so halfway up to 50 is at 25. So let me try and get as close to 25 as I can. That wasn't bad. I draw across, and I get, see where it touches the polygon, and then I try and draw down from there. That's pretty much 70, man. That's pretty much like a 70. I'm just going to say 70. It's close enough. Okay, so that's going to be 70. Like maybe 70, 71. I don't know. Alright, we'll go 71. Okay. Which class interval did the upper quartile occur in? So upper quartile means we want to go halfway between these two now. Okay, so upper quartile is a median of this half. So what's halfway between 25 and 50? That's going to be 37.5. So there's my 35, 37.5. That's going to be right here. Oh, let's see if I can keep this up. Put it down. There we go. Alright, so it's going to go here. Okay, now this is just asking for class intervals, so I don't have to be overly precise with that, but you know what, I can draw that one down, and that class interval is between 70 and 80. So 70 to 80. Okay, so 75 is the middle, so it's 70 to 80. That's the class interval, that bucket there. Okay, maybe fill this in, make it look a bit prettier. Okay. How many students failed the examination, so achieved below 50%? Well, this is a running total of scores, so if I look at the complete running total up to 50%, that's the number of students there then. Okay, I don't have to add these two because this already is a running total count. Okay, so I don't have to add up, they're not separate counts. Okay, this includes all of those guys as well. So that's going to be, I reckon that's, what, 12? 12 students? Okay. So maybe I should label what's going on there. We'll put it here. Okay, so that's my 12 people who failed. Okay, because that's my 50% cutoff right there. Okay, how many students achieved a mark between 50 and 60? Well, that's a bit different because between 50 and 60 means how many students were inside this range here, how many guys were in there, right? Again, this is a running total, so you can't just count how many people are here because this includes both of these guys. So to see how many students actually were in this sort of bucket, we have to see how much that the running total got increased by. Okay, so it was 12, now it's 20. That's an increase of 8. And so that tells you that 8 students were in this bucket. That's why the running total got increased by 8. So that means it's going to be 8 students. Okay, so that's how you get the, you can read off frequencies from cumulative by doing that. Alright, 2 class tests, Terry and Kim, so the results are placed there. Write down Kim's 5 numbers summary. So lowest mark 67, that mark 69, that's my first quartile, median 71, upper quartile 73, upper end, is that like a bit under 70? I'll just say it's 75. It's close enough. 75. Okay, what percentage of Terry's results were below 69? Well, below 69, there's Terry's median is 69. So below 69 has one section there and one section there. Remember, for a box and whisker plot, each of these sections is worth 25%. So 2 sections would be worth 50%. Okay, every section of a box and whisker plot is worth 25% of the scores. Okay, so Terry claims his results were better than Kim's. Is he correct? Well, we better compare all those things. So the medians, who got the higher median? Oops. Who got the higher median? So who had the higher center? So Kim wins on that one. So Kim is median. How much higher? Her one's 71, Terry's one's 69, so it is 2 marks higher. Which means sort of middle, sort of on average-ish. She probably did better, okay, but we can look at other things as well. What about the spread of marks? Okay, so how spread were they? Interquartile range. So who had the biggest spread of marks? Well, interquartile range is the length of the box. Okay, so I'll make a note of that. This is the box length, because that tells you exactly the difference between upper quartile and lower quartile. Okay, the Q3 and Q1. The box length tells you that gap. So Kim's interquartile range is, well, what's the interquartile range here? It's 4, so 69 and 73. That's a gap of 4. Whereas Terry's is from 68 to 74. That's a gap of 6. So her interquartile range is 2 marks lower. Is that a good thing or a bad thing? Is it a good thing or a bad thing that her spread is lower? Well, it's a good thing for marks, because if the spread is lower, that means she's more consistent. Okay, so her sort of middle average-ish is kind of higher, and she's more consistent. And so the shape of a distribution as well, I would say, well, Kim's one distribution is symmetric. Just look at her plot, it's completely symmetric. Whereas Terry's one How would you describe that? It's heavy on the left side, and there's a tail end. Okay, so half of his scores are stacked inside this little region here. Half of them are stacked in there. The other half are spread out over there. So if you had to plot Terry's sort of distribution, you would have a lot of things in the lower end, and then like a tail on the upper end, and what we call that is positively skewed. So his distribution is positively skewed. Now here's one of those cases where math terminology is terrible. Positively skewed is actually a pretty bad thing. Okay, because what does it mean? Positive skew. Look at the shape. It means most of his marks are bad. Just got lucky or something a couple of times up here, but most of his marks are bad. It's all piled up down there. So his distribution being positively skewed is a bad thing. Okay, so what does this mean? His marks are mostly on the low end. Okay? Because that's what the distribution says. A lot of stuff piled on the low end and a few things up top. Okay? So, what's our conclusion then? Kim probably did better. So Terry is wrong. Okay? She had the higher median. She was more consistent. His distribution was terrible because it showed that his marks were mostly on the low end. Okay, so he is wrong. Sorry about that. He's wrong. Sorry, I don't know what I'm doing. I'm just messing around. Alright, burrito chart. How many customers reported missing buttons? Again, this is quite a mean chart because it's not very precise. You just do your best here, okay? So how many reported missing buttons? Well, that's 200. That's 300. So what would you say that is? That's maybe about 220-ish. So if you're at something different, if you're close enough to that, that's fine. Okay. Important thing with these is that the bars count actual frequency, the line counts cumulative percentage. So what percentage of customers reported stitching errors? So just like our cumulative thing before, you can't just read the percentage. You can't just say, oh, that's about 60, 67. You can't do that, okay? Because this is a running total. So to see how many people were in this reported stitching errors here, you have to see what's the contribution to that running total. Okay, so if it used to be here, what's the contribution going up to there? So let me draw some lines to make that a bit easier. Okay, if that one used to be there, what's the contribution of that coming up to there? Okay, so over here, how much did the stitching errors increase that running total by? And what would we say? It's about 100. Alright, it's about 100. Again, in your tests and stuff, I think the graph will be more exact. Okay. Oh, sorry, it's not 100. It's the percentage. So it's about that would be about 20 and a bit. So what do you reckon, about 20, 25-ish maybe? So 20, 40, 60, 80, 100, yeah. It's about 25. Sorry about that. It's a percentage I'm looking for. Okay, so estimate the percentage of customers reporting hemming errors. So same thing. So we're looking at the percentage that it's increasing by from there to there. So again, we can draw two lines. We want to think about that. Increasing to there. Okay, so what contribution did the hemming errors have to this running total? Look, that's about half of the bar, so I will say about 10%. Which defects accounted for 80% of the customers' reports? So I need to see when have I covered 80% of all the complaints. It seems that at this point here, my running total has covered 80%, which means I just have to, which defects is it? It's the missing button, the stitching errors, and the loose thread. Okay, so main thing with this chart is the bars are actual counts, actually about 220, actually about 110, 20, whatever it is. Okay, but the line is a cumulative percentage, which means it's a running total of the percentage. Okay, so that point there tells me that 80% is accounted for by adding up these three things: missing button, stitching errors, loose thread. Also means that to get one percentage, like the one we did before, you have to see how much percent contribution does it make to the running total. Okay. Alright, so that's the data stuff. See you in the next one.